In this lesson, you'll learn how to read text data from different sources and prepare it for feature extraction. You'll begin by cleaning it to remove irrelevant items such as HTML tags. You'll then normalize text by converting it into all lowercase, removing punctuations and extra spaces. Next, you will split the text into words or tokens and remove words that are too common, also known as stop words. Finally, you will learn how to identify different parts of speech, named entities, and convert words into canonical forms using stemming and lemmatization. After going through all these processing steps, your text may look very different, but it captures the essence of what was being conveyed in a form that is easier to work with.
The processing stage begins with reading text data. Depending on your application, that can be from one of several sources. The simplest source is a plain text file on your local machine. We can read it in using Python's built-in file input mechanism. Text data may also be included as part of a larger database or table. Here we have a CSV file containing information about some news articles. We can read this in using pandas very easily. Pandas include several useful string manipulation methods that can be applied to an entire column at once. For instance, converting all values to lowercase. Sometimes you may have to fetch data from an online resource, such as a web service or API. In this example, we use the requests library in Python to obtain a quote of the day from a simple API. But you could also obtain tweets, reviews, comments, whatever you would like to analyze. Most APIs return JSON or XML data, so you need to be aware of the structure in order to pull out the fields that you need. Many datasets you will encounter have likely been fetched and prepared by someone else using a similar procedure. Text data, especially from online sources, is almost never clean. Let's look at the Udacity course catalog as an example. Say you want to extract the title and description of each course or nanodegree. Sounds simple, right? Let's jump into Python and give it a shot. You can follow along by downloading and launching the text processing notebook. We can fetch the web page like any other online resource using the requests library. It looks like we got back the entire HTML source. This is what the browser needs to render the web page, but most of this is useless for our purposes. We need a way to extract all the plain text as visible on the website. How about using regular expressions? Let's define a pattern to match all HTML tags and remove them by replacing with a blank string. Okay, that did something. We can see that the page title has been extracted successfully, but there's a lot of JavaScript and a number of other items that we don't need. In fact, this regular expression somehow didn't match some tags. Maybe they were nested inside other tags. Maybe we need to account for tags spread across lines. Anyway, this doesn't seem like the best approach for this job. What we really need is a way to parse the HTML, just like a web browser, and pull out the relevant elements. Introducing Beautiful Soup. It's a nice Python library meant to do exactly that. You just pass in the raw web page text, which in this case contains HTML, to create a soup object. And then you can extract the plain text, leaving behind any HTML tags, using a simple call to the getText method. This takes care of nested tags, tags that are broken across lines, and a multitude of other edge cases that make HTML parsing a pain. It also forgives some small errors in HTML, just like browsers, making it more robust. Let's see. That's better. I don't see any HTML tags, but there's still a bunch of JavaScript and a lot of spaces. What else can we do? Let's take a look at how the HTML source is structured. The easiest way to do this is to right-click on an element of your choice, here this course title, and choose Inspect or View Page Source. Now look at where the title is placed and what is the most distinct way of finding it in the HTML document tree. Here we have a parent div with a class of Course Summary Card. That sounds promising. Let's use it. Beautiful Soup is actually very powerful. It enables you to walk the tree or DOM in many different ways. Here we are asking the library to find all divs with a class of course summary card. The result returned is a list of all such divs in the document. Let's store this in a variable and look at one of the divs. Okay, scrolling through this, I see that the title is stored in this A tag, which is contained in this H3 tag. How do we extract this title? One way to get to it is using a CSS selector. Aha! And now we can fetch the plain text content just like we did before. Great! One last thing, let's strip out the extra white space from both ends. There you go. Now, let's look back at the HTML to see how we can grab the description text. There it is. It's a div with an attribute called Data Course Short Summary, but no value or any other attribute. Again, there is a way to select such tags using CSS. Specify the tag name, here div, followed by the attribute name in square brackets. Looks good. Let's extract the text and clean it up. All right, we can now repeat this over all course summaries. To do this, we can use a simple for loop. Looks spot on to me. Let's store this data so we can use it later. Here we are simply keeping the data in a list called courses. What we did just now is called scraping a web page. Although it sounds a little violent, trust me, it's not. In fact, scraping is very common. Google News is a prime example. It pulls out the title and first sentence or two from news articles and displays them. Google probably uses a combination of rules and machine learning to identify what portion of the HTML contains the title and the beginning of the article text that it can use as a preview. It works great most of the time, but sometimes it does fail. Here, for this article on quantum entanglement, the preview doesn't seem to match the title at all. It looks more like a caption for this image. What likely happened is that the caption was the first piece of text on the web page, and Google's algorithm picked that up as if it was part of the main article. This just goes to show how seemingly routine tasks in text processing are still not solved all the way. Okay, let's look back at what we just achieved. We started by fetching a single web page, the Udacity course catalog. Then we tried a couple of methods to remove HTML tags. We finally settled on using Beautiful Soup to parse the entire HTML source, find all course summaries, and extract the title and description for each course. And then we saved them all in a list. Depending on what you're planning to do next, you may continue to treat these chunks as part of a single document, or consider each to be a separate document. The latter is useful, for instance, if you want to group related courses. The problem then reduces to document clustering. Plain text is great, but it's still human language with all its variations and bells and whistles. Next, we'll try to reduce some of that complexity. In the English language, the starting letter of the first word in any sentence is usually capitalized. All caps are sometimes used for emphasis and for stylistic reasons. While this is convenient for a human reader, from the standpoint of a machine learning algorithm, it does not make sense to differentiate between car, and car. They all mean the same thing. Therefore, we usually convert every letter in our text to a common case, usually lowercase, so that each word is represented by a unique token. Here's some sample text, a review for the movie The Second Renaissance, a story about intelligent robots that get into a fight with humans over their rights. Yep, the way we treat robots these days. Anyway, if we have the review stored in a variable called text, converting it to lowercase is a simple call to the lower method in Python. Here's what it looks like after conversion. Note all the letters that were changed. Other languages may or may not have a case equivalent, but similar principles may apply. Depending on your NLP task, you may want to remove special characters like periods, question marks, and exclamation points from the text. and only keep letters of the alphabet and maybe numbers. This is especially useful when we are looking at text documents as a whole in applications like document classification and clustering, where the low-level details do not matter a lot. Here we can use a regular expression that matches everything, that is, not a lowercase a to z, uppercase a to z, or digit 0 to 9, and replaces them with a space. This approach avoids having to specify all punctuation characters, but you can use other regular expressions as well. Lowercase conversion and punctuation removal are the two most common text normalization steps. Whether you need to apply them and at what stage depends on your end goal and the way you design your pipeline. Token is a fancy term for a symbol, usually one that holds some meaning and is not typically split up any further. In case of natural language processing, our tokens are usually individual words. So tokenization is simply splitting each sentence into a sequence of words. The simplest way to do this is using the split method, which returns a list of words. Note that it splits on whitespace characters by default, which includes regular spaces, but also tabs, new lines, etc. It's also smart about ignoring two or more whitespace characters in a sequence, so it doesn't return blank strings. But you can control all this using optional parameters. So far, we've only been using Python's built-in functionality, but some of these operations are much easier to perform using a library like NLTK, which stands for Natural Language Toolkit. The most common approach for splitting up text in NLTK is to use the word tokenize function from nltk.tokenize. This performs the same task as split, but is a little smarter. Try passing in some raw text that has not been normalized. You'll notice that the punctuations are treated differently based on their position. Here, the period after the title doctor has been retained along with DR as a single token. As you can imagine, NLTK is using some rules or patterns to decide what to do with each punctuation. Sometimes you may need to split text into sentences, for instance, if you want to translate it. You can achieve this with NLTK using sent tokenize. Then you can split each sentence into words if needed. NLTK provides several other tokenizers, including a regular expression-based tokenizer that you can use to remove punctuation and perform tokenization in a single step, and also a tweet tokenizer that is aware of Twitter handles, hashtags, and emoticons. Check out the nltk.tokenize package for more details. Stop words are uninformative words like is, are, the, in, at, etc. that do not add a lot of meaning to a sentence. They are typically very commonly occurring words, and we may want to remove them to reduce the vocabulary we have to deal with and hence the complexity of later procedures. Notice that even without are and the in the sentence above, we can still infer its positive sentiment toward dogs. You can see for yourself which words NLTK considers to be stop words in English. Note that this is based on a specific corpus or collection of text. Different corpora may have different stop words. Also, a word may be a stop word in one application but a useful word in another. To remove stop words from a piece of text, you can use a Python list comprehension with a filtering condition. Here we apply stop word removal to the movie review after normalizing and tokenizing it. The result is a little hard to read, but notice how it has helped reduce the size of the input. At the same time, important words have been retained. Remember parts of speech from school? Nouns, pronouns, verbs, adverbs, etc. Identifying how words are being used in a sentence can help us better understand what is being said. It can also point out relationships between words and recognize cross-references. NLTK again makes things pretty easy for us. You can pass in tokens or words to the POS tag function, which returns a tag for each word, identifying different parts of speech. Notice how it has correctly labeled the first occurrence of lie as a verb, while marking the second one as a noun. Refer to the NLTK documentation for more details on what each tag means. One of the cool applications of part-of-speech tagging is parsing sentences. Here is an example from the NLTK book that uses a custom grammar to parse an ambiguous sentence. Notice how the parser returns both interpretations that are valid. It is much easier to see the difference when we visualize the parse trees. I shot an elephant in my pajamas versus I shot an elephant and the elephant was in my pajamas. How he got into my pajamas? I don't know. Named entities are typically noun phrases that refer to some specific object, person, or place. You can use the ne_chunk function to label named entities in text. Note that you have to first tokenize and tag parts of speech. This is a very simple example, but notice how the different entity types are also recognized. Person, organization, and GPE, which stands for geopolitical entity. Also note how it identified the two words Udacity and ink together as a single entity. Out in the wild, performance is not always great, but training on a large corpus definitely helps. Named entity recognition is often used to index and search for news articles, for example, on companies of interest. In order to further simplify text data, let's look at some ways to normalize different variations and modifications of words. Stemming is the process of reducing a word to its stem or root form. For instance, branching, branched, branches, etc. can all be reduced to branch. After all, they convey the idea of something separating into multiple paths or branches. Again, this helps reduce complexity while retaining the essence of meaning that is carried by words. Stemming is meant to be a fast and crude operation, carried out by applying very simple search and replace style rules. For example, the suffixes ing and ed can be dropped off, ies can be replaced by y, etc. This may result in stem words that are not complete words, but that's okay as long as all forms of that word are reduced to the same stem, thus capturing the common underlying idea. NLTK has a few different stemmers for you to choose from, including Porter stemmer that we use here, Snowball stemmer, and other language-specific stemmers. You simply need to pass in one word at a time. Note that here we have already removed stop words. Some of the conversions are actually pretty good, like started reduced to start. Others, like people losing the E at the end, are a result of applying very simplistic rules. Lemmatization is another technique used to reduce words to a normalized form. But in this case, the transformation actually uses a dictionary to map different variants of a word back to its root. With this approach, we are able to reduce non-trivial inflections such as is, was, were back to the root B. The default lemmatizer in NLTK uses the WordNet database to reduce words to their root form. Let's try it out. Just like in stemming, you initialize an instance of WordNet lemmatizer and pass in individual words to its lematize method. What happened here? It seems that only the word once got reduced to one. All the others are unchanged. If you read the words carefully, you'll see that once is the only plural noun here. In fact, that's exactly why it got transformed. A lemmatizer needs to know or make an assumption about the part of speech for each word it's trying to transform. In this case, WordNet lemmatizer defaults to nouns, but we can override that by specifying the POS parameter. Let's pass in V for verbs. This time, the two verb forms boring and started got converted. Great! Note that there are other verbs, but they're already in the root form. Also note how we passed in the output from the previous noun lemmatization step. This way of chaining procedures is very common. Let's recap. As we saw in the previous examples, stemming sometimes results in stems that are not complete words in English. Lemmatization is similar to stemming with one difference. The final form is also a meaningful word. That said, Stemming does not need a dictionary like lemmatization does. So depending on the constraints you have, stemming may be a less memory-intensive option for you to consider. We have covered a number of text processing steps. Let's summarize what a typical workflow looks like. Starting with a plain text sentence, you first normalize it by converting to lowercase and removing punctuation. And then you split it up into words using a tokenizer. Next, you can remove stop words to reduce the vocabulary you have to deal with. Depending on your application, you may then choose to apply a combination of stemming and lemmatization to reduce words to their root or stem form. It is common to apply both, lemmatization first and then stemming. This procedure converts a natural language sentence into a sequence of normalized tokens which you can use for further analysis.